Alright, so this is going to be attempt 394 to do a video. We're going to be starting Unit 3. So in your notes, I would start with a fresh sheet of paper. Unit 3, and this is going to be 3, oh, great already. This is going to be 3.1, and we're going to be talking about exponential functions. And also logistic functions. So to start this section, we're going to talk about an exponential function first, and exponential functions are always written in the form f of x equals a times b to the x. So this is a little bit different than we've seen before. We're used to seeing variables in the equation itself. This time the variable is the exponent. A is always non-zero, and b is always positive, and b is never equal to 1. So a is non-zero, b is positive, and never equal to 1. We also have the letter a. We call that the initial value. And that's always when x is equal to 0. And we have b, which we always call the base. And that's my dog. So another thing too about the initial value is a lot of times that it'll be written as something sub-zero. So maybe like p sub-zero or capital B sub-zero. The sub-zero always stands for initial value. So let's try a couple of examples of identifying exponential functions. If we have an example like 3 to the x. f of x equals 3 to the x. Is this an exponential function? Yes. It is an exponential function because we have an initial value of 1, because really it's 1 times 3 to the x, even though we don't write it. And we have the base equal to 3. Let's try another example. 6x to the negative 4. Is this one an exponential function? This is not an exponential function because the base cannot be a variable. So our initial value in this case would have been 6. Would have been 6 times this. But our base is x. And the base is not allowed to be a variable, so this is not an exponential function. Let's try another one. How about negative 2 times 1.5 to the x? Is this an exponential function? Yes, this one is an exponential function with initial value negative 2. So our a value is negative 2, and then our base is 1.5. Because 1.5 is raised to the x, 1.5 has to be our base. And we're going to do 2 more examples here. This one is a little bit trickier. It's 7 times 2 to the negative x. Would this one be an exponential function? Yes, it is an exponential function. Again, 7 is our initial value. It's our a value. And then our base value actually isn't going to be 2. Because we have a negative exponent, we need to get rid of that negative exponent. And we've talked about negative exponents before. What does this actually mean? Well, this actually stands for 2 to the negative 1 times x. Right, I can do that. And then 2 to the negative 1 is actually really 1 over 2 to the x. Remember, that gets moved to the bottom. We talked about that in, I believe, the first unit. So now we actually have, and I'm just going to rewrite my 7 down here. Now I actually have 7 times 1/2 to the x. So still 7 is my initial value, but in this case my base is 1/2. And we're going to do one more example here. The last example is going to be 5 times 6 to the pi. Is this one an exponential function? No, this is not an exponential function because pi is actually a constant. It's not a variable. In order for it to be an exponential function, it has to be the exponent has to be a variable, just like in these cases up here. In this case, pi is not a variable. Pi, we know pi to be 3.1415, blah, 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 blah. So it's not ever going to change. Pi is always going to be exactly the same. So this is not an exponential function. Next, we're going to learn how to evaluate exponential functions. So in this case, we're going to talk about the most basic one that's used, I would say probably most. F of x equals 2 to the x. So now I want you to evaluate f of 4, f of 2, f of 0, f of negative 3, f of 1/2, and f of negative 3/2. So remember, whatever the of f of 4, that's our x value. So now all I'm going to do is substitute that number in for x. So in this case, I'm going to have 2 to the 4, which is really the same as 2 times 2 times 2 times 2, right? And that's really the same as 16. So f of 4 is equal to 16. Same thing here. I'm just going to substitute in my x value, 2 squared. And that's really 2 times 2, which we all know is 4. F of 0. So this is actually my favorite exponential function because remember, anything raised to the 0 power is always equal to 1. And a lot of times that'll really help us out, and it's going to be really important when we talk about modeling a little bit later on. F of negative 3. So again, I'm just going to write it in as x, but we don't like negative exponents and we can't solve them, so we have to fix it. And how do we solve a negative exponent? We do 1 over the base to the positive exponent. And we know that 2 to the third is 8, so this is really the same as 1 over 8, or 0.125. The next one, we have 2 to the 1/2. And remember, when you have a fraction, it's always the base raised to the numerator, and then you're taking the, in this case it's going to be the square root because the denominator is 2, but if the denominator was 7 or 5 or 4, you would take whatever that number is, root of it. So we'll see what that looks like in this next one here as well. So this is actually going to be just the square root of 2, which is approximately, remember it's an irrational number, it's approximately 1.414, blah, blah, blah. And then the last one, we have 2 to the negative 3/2. So before we do anything, we got to get rid of that negative exponent first. And how do we do that? 1 over 2 to the 3/2. And after we do 1 over 2 to the 3/2, we can fix this. Remember, we leave it raised to the numerator, and then we take the whatever the denominator is, root of it. So in this case, we're going to take 1 over, this is going to be the square root of 2 to the third. And we just said up in this example up here that 2 to the third was 8, so square root of 8. And you can either do that on your calculator, or you can reduce it down to 1 over 2 root 2, which is the same as 0.35355. So these are examples of how to evaluate exponential functions. Unfortunately, we don't have a way to evaluate an exponential function for irrational inputs, but we can get really close using rational approximations. So what does that mean? Well, for example, if we use pi, we know that pi is an irrational number, right? We don't actually know what pi is equal to. It's equal to about 3.14159, blah, 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 blah. Goes on forever and ever. So in order to approximate this, or in order to evaluate this something to the pi, we have to approximate it using numbers that we actually know. So in this case, if I'm going to use that same expression, remember from the last slide, it was f of x equals 2 to the x. We're going to use that same one here. So in this case, I would have f of pi equals 2 to the pi. Well, I really can't do that because pi is irrational. So what we're going to do is make a table of values. I'm going to put my x values on this side and my f of x values on this side. So we're going to start with an easy one. So we'll just do the regular function that we're using, and the function that we're using again is 2 to the x. Then I know that pi starts with 3. It's 3 point something. So I'm going to use 3 for my first value. If I substitute 3 in for x, I get 2 to the third, which is actually 8. So I'm kind of getting closer to my rational approximation. Then I know it's 3.1, so I'm going to do 3.1 here. Then I can do 3.2 to the 3.1. And that's approximately, and again, these are all going to start to be approximations. That's approximately 8.5, blah, blah, blah. And then I know it's 3.14, so I can do 2 to the 3.14. And that's approximately 8.81. 3.141. So if I do 2 to the 3.141, it's going to be approximately 8.821. 3.1415. Same thing, this kind of gets a little bit redundant here. Oops. And we get 8.8244 this time. And the last one I'm going to do is 3.14159. And now you could keep going because we know that pi goes on forever and ever. So you could feasibly keep going. But I'm going to stop right here because we have a pretty good approximation now. 2496. So you can kind of see that we're getting closer and closer and closer and closer each time. So it changes pretty drastically the first couple of times because we're only going out to the tens place here and the hundreds place here. We're not getting really, really close. As we have more decimal places, we're going to start to get really close. So now, what I would say is, okay, it looks like I have 8.8, 8.8, 8.8. Good. 8.2 starts to show up a lot, and I bet if I kept going, 8.2 would continue to show up. So I'm going to say that that's a pretty good approximation, and I can say that 2 to the pi is approximately equal to 8.82. And now on a test or quiz, I would definitely specify what I want you to approximate to. In this case, I approximated to 2 decimal places, and that's generally what we try to do. But on a test or quiz, it will have that written for you. Alright, in this next part, you may be given a table, and you have to find the formula for the exponential function. So, in this case, we're going to do two examples in one, so I can just make one table altogether. We're going to use the same x values anyway, so this is going to be my x, this is going to be my g of x, maybe, and this is going to be my h of x. Again, it doesn't really matter what you use for letters here, it's just to differentiate. In the last couple of slides we've been using f of x, so I'm going to change it up just a little bit so we don't get confused. The x values that we're going to use are -2, -1, 0, 1, and 2. We're going to use it for both functions, and now these are going to be two completely different functions. We're just doing two examples at the same time. So on a test or a quiz or in a question on homework, you would be given the table. So I'm just going to quickly write out the table. That's 4/9. This is 4/3. This is going to be 4. This is 12 and 36. And then for a different problem, you might have something like 128, 32, 8, 2, and 1/2. So just in case I lost you a little bit here, this is two different examples, and this is what I get. These numbers are what I get when I substitute in my x value. -2 for g of x, I get 4/9. For h of x, I get 128. So these are two separate problems here. So what you're going to do, given a table, so basically we're working backwards now. We want to try and figure out what the exponential function is, or what the formula for the exponential function is. How did they get from this first one, from this first one to the second one? Sometimes it's easier if you start with ones down here, because fractions are sometimes difficult for people. So let's go, how did they get from 4 to 12? They multiplied by 3. How did they get from 12 to 36? They multiplied by 3. Now you can go back up here and say, oh yeah, that's right, they did. They multiplied by 3. And then from here to here, they multiplied by 3. So I'm going to leave that example alone. I'm going to go to the second example now. Now let's figure out what they did to get from 128 down to 32. So we still are multiplying, but we're not going to be multiplying by a whole number. We're going to be multiplying by a fraction. Remember, multiplying by a fraction means that you're going to decrease the value. So in this case, we're multiplying by 1/4, multiplying by 1/4, multiplying by 1/4, or the same as dividing by 4, remember? Multiplying by 1/4. Alright, so now we have all the information that we need, and we can write our equations. Go back to the very, very first thing that we wrote in our notebook. We said that an exponential function, I'm just going to write it over here in the blue, you might be able to see it, f of x, f of x is equal to a times b to the x. We said that a is always the initial value and b is always the base. So watch very carefully. This is what you're always going to do for problems like this. In order to do g of x, I'm going to write g of x is equal to, what's my initial value? Well, if you look back in your notes, we said that the initial value is what happens when x is equal to 0. So I look back at my table and I say, okay, x is equal to 0 here. The initial value must be 4. So my a value in this case is 4. Now let's find the b value. Well, the b value is the base. And the base is always what we're multiplying by, or the factor that you're multiplying by every single time. So in this case, our b value is going to be 3. And my exponential stays the same because I always have to have it raised to a variable. So now you try h of x. First you want to find your initial value, then your b value, raise it to the x. Well, my initial value is 8, because I find when x is equal to 0, my initial value must be 8 right here. and I multiply that by my base, which in this case, the factor that I'm multiplying by every single time is 1/4. So I'm going to put that in parentheses. 1/4 raised to my exponent. Those would be, we did 2 examples, those would be your 2 answers for those 2 examples. In this next part, we're going to talk about exponential growth and decay, and I know you talked about this in Algebra 1 and Algebra 2, and now we're going to do it again in Pre-Calc. So exponential growth and decay, we're still using that same equation, or that same function, f of x equals a times b to the x. When we talk about exponential growth, remember our a value is always going to be bigger than 0. We said right in the beginning, the very first notes we took said that the a value is always non-zero. So in this case, we want to have positive a values in order for this to work. So when a is bigger than 0, and when the base b is bigger than 1, remember b can never be 1. So when a is bigger than 0 and b is bigger than 1, we have exponential growth. Going along with that, our b value, whatever that b value happens to be, is called the growth factor. And normally when we talk about exponential growth, we always talk about exponential decay. So in the same case, again, be really careful here. A is bigger than 0. So a is bigger than 0 for both of these, because otherwise if it's negative, it's going to flip the whole equation around. We talk about reflections and whatnot, so we want a to be bigger than 0, or a to be positive in both of these cases. So when a is bigger than 0 and b is less than 1, remember again, b cannot be 1, but when b is less than 1, then we experience exponential decay. And same thing, we have again that b is now going to be called our decay factor. So I'm just going to go back to the slide that we were just on where we found the functions for these 2 different equations. Let's look at g of x. A is bigger than 0 and b is bigger than 1. So is this function going to be exponential growth or exponential decay? It's going to be exponential growth because a is bigger than 1 and b is bigger than 1. So we're going to have exponential growth there. Look over here at our second example, h of x. Is h of x going to be exponential growth or exponential decay? Again, a is still bigger than 0 here, but look at our b value this time. b is less than 1. Since b is less than 1, this is going to be exponential decay. In our g of x function, our growth factor is 3. In our h of x function, our decay factor is 1/4. And now this pretty much makes sense because look, our growth factor is 3. We're growing by a factor of 3 each time. Factor means to multiply. So multiplying by 3 each time, we're growing by a factor of 3 each time. In this case, we're decaying by a factor of 1/4 each time. Going down by a factor of 1/4. When we multiply by a fraction, we're getting smaller and smaller and smaller. So that makes sense that that's a decay factor. And I'll go back to that in case you didn't grab those notes. And finally, the last part, and this is going to be just the first video of section 3.1. This is the last thing that we're going to talk about in this half of this section. Transformations. So remember transformations: vertical shift, horizontal shift, reflections, and then rotations and whatnot like that. We're going to talk about vertical stretches and shrinks and compressions, and just like we did in the last chapter as well. Translations. So you want to kind of take a second to go back to your notes about translations, because we're going to be talking about them a lot. In these examples, we're going to translate the same function that we've been working with, f of x equals 2 to the x. So in the first example, I'm going to call this letter A. I want you to tell me how I get from my original function to 2 to the x minus 1. How do I get from 2 to the x to 2 to the x minus 1? What happens to my graph? And you can graph this on your calculator if you want, or if you remember your rules, since we're changing something about our x value, it's going to be a horizontal shift. But which direction? Remember when we talked about horizontal shifts, it always was the opposite of what we're doing. So you would think that it would be to the left, but since it's horizontal, we're actually going to go to the right. So you're shifting right 1 unit. The next example here, I'm going to call it B, if I can figure out how to write. There we go. This is going to be 2 to the negative x. So again, we're doing the opposite of our x value. So it's going to be something that has to do with horizontal. And the way we reflect something horizontally is we reflect it over the y-axis. So in this case, this is going to be a reflection over the y-axis. And then this is just going to be the last example for this section here. Letter C. The function is going to be 3 times 2 to the x. So we know this is an exponential function. Again, a is our initial value here. B is 2. That's our base. But how did I get from 2 to the x to 3 times 2 to the x? We didn't do anything this time to our x value. Notice in these two, we did something to our x value. We left it alone this time, and we actually changed the entire function. When we change the entire function, it's going to be a vertical change. So we're actually going to be stretching this vertically by a factor of 3. This is a vertical stretch. By a factor of 3. And you are halfway through section 1 of our third unit, 3.1. Check out the next video for the second half of section 3.1.